In the last video, we ended on this problem. The problem says, are these vectors linearly independent? And we said the answer was no, they're linearly dependent. And how we showed this is we took these three vectors and multiplied them by c1, c2, c3 and added them up and set it equal to 0, the 0 vector. And in order for these vectors to be linearly independent, c1, c2, and c3 have to all equal 0. That's the only way for this sum to give us the 0 vector. But if they're linearly dependent, then we can find a c1, a c2, or a c3 that's non-zero, and we get this 0 vector. So we notice that solving this for the c1, c2, c3 is the same thing as solving the system. And what we can do is we can make an augmented matrix where we take the coefficients of this system, everything to the left of the equal sign, and that being the matrix A, which is the same thing as just putting these three vectors as columns in A. And we can set x equal to c1, c2, c3. And if we do that, what we're doing is we're solving this system here. A times x is equal to 0. And what I mean by solving the system, that means we're looking for all solutions x, c1, c2, c3, that when I plug it in here, I get a times x is equal to 0, which is exactly the null space. Now, in order for our vectors to be linearly independent, that means that the only solution we can get for x is 0. And that's because we have to have n pivots. And here, the null space, if we only have one solution, the null space is going to be the 0 vector. So we did this. Here's the matrix A. Here's the 0 vector. We put this in reduced row echelon form. We noticed that we only had 2 pivots. So we solved for those pivots. We got c1, c2, c3. And we saw that c3 is a free variable, and c1 and c2 depend on c3, which lets us write the null space. The null space, if we substitute r in for c3, we get that r times -3, -1, 1, where r is anything that should be in the real numbers, not the integers. This is the null space, which we can find a spanning set, which is just this vector here. And we can see that the null space is not just the 0 vector, which tells us that these vectors are not linearly independent. They're linearly dependent. Now, what if I have k vectors in our vector space Rm? How can I tell if they're linearly independent? Well, we're going to build on what we just did. What I'm going to do is I'm going to make a matrix A, which consists of these column vectors. And this matrix is m by k. Why is it m by k? Well, if I put V1 here, it's going to have m entries because it's in Rm. So that means each one of these is going to have m entries, so I would have m rows. And because I have k vectors, each one of these is a column, you can see that I have k columns. So if I want to figure out if these vectors are linearly independent, well, I would need to have one solution to a times x is equal to 0. So to have one solution, that means A has to have k pivots. Because remember, x corresponds to c1, c2, all the way to ck. The coefficients in front of these vectors. And they all have to be equal to 0, so you would have to have k pivots. So A has k pivots in reduced row echelon form. If you have less than k pivots, then you have infinitely many solutions. which is the same thing as saying the null space is not equal to just the 0 vector. If you have k pivots, then the null space is the 0 vector. Here we're going to look at a theorem and be very specific in this theorem. Suppose that we have n vectors in Rn. Okay, compare this to what I just said a minute ago. Before, I had k vectors in Rm. I want these two numbers to be the same. I want n vectors in Rn. Then v1 through vn is linearly independent if and only if we make this matrix A equal to, where the columns are the vectors, is going to be a square matrix because we're going to have n rows and n columns. So these vectors are linearly independent if and only if A is invertible. Why is this? Well, A is n by n. And remember, we're going to have n C's because we have C1 V1 plus C2 V2 all the way to Cn Vn. We want that to equal 0. So X, remember, is C1, C2, all the way to Cn. I'm putting this as the transpose of this. You need n pivots in order for each one of these to be equal to 0. Well, if you have n pivots in an n by n matrix, that means A has to be row equivalent to the identity matrix. Because when you put it in reduced row echelon form, it has to be the identity matrix. And if a matrix is row equivalent to the identity matrix, then it's invertible. Now remember that if this matrix is not square, then we can't talk about a matrix being invertible or not. We don't have a definition for a matrix being invertible if it's not square. So you have to be very careful. You have to have the same number of vectors as this number here in Rn. Let's look at an example. Are these vectors linearly independent? I want to use the theorem I just showed you. Well, notice that I have 3 vectors in R3. So I can use my theorem. Well, these are linearly independent if A equal to 1, 2, 0, 1, negative 1, 3, 2, 1, 3 is invertible or non-singular. Now there's several ways to figure this out. We could do what we did before, which is just put this in an augmented matrix and find the reduced row echelon form and see if the reduced row echelon form is the identity matrix. If it is, then these vectors are linearly independent. However, I'm going to use another theorem. I know that a matrix A is invertible if it's square, then its determinant is non-zero. So if I take the determinant of this matrix and I get anything other than 0, then it's invertible, which would mean by the last theorem that these vectors are linearly independent. So let's see. Let's take the determinant of this matrix. So the determinant of A is equal to, I'm going to go along this column. This is 1, negative 1 to the 1 plus 1, determinant of negative 1, 1, 3, 3, plus 2, negative 1 to the 2 plus 1, determinant of 1, 2, 3, 3, and then plus 0 times some stuff, but 0 times anything is 0. So we really only need this piece. This is equal to 1, negative 3 minus 3, minus 2, 3 minus 6, which is negative 6 minus 2 times a negative 3. I get negative 6 plus 6, which is 0. That tells me A is not invertible. And since that is the case, our vectors are not linearly independent. Now, what we've done has only told us if it's linearly independent or linearly dependent. If I actually ask you to find the C1, the C2, and the C3, then you have to put it in reduced row echelon form to figure that out. Okay, I have a trick question for you. For any vector space V, we know we have the 0 vector in V. Is 0 linearly independent? It seems strange, right? I only have one vector, and I'm asking if this vector is linearly independent. Let's use the definition. If I put the 0 vector here, and I put a scalar in front of it, well, for it to be linearly independent, this is true if and only if C1 is equal to 0. Well, it's linearly dependent if C1 can be non-zero. Obviously, you could put 1 here. You could say 1 times 0 is equal to 0. In fact, any scalar times the 0 vector is going to give you the 0 vector. So 0 is linearly independent. Oh, sorry, linearly dependent. Why I think that's weird is because when we say linearly dependent, if we have 3 vectors, we say they're linearly dependent, then one of them depends on the other 2. But here you have the 0 vector depends on itself, so it's kind of like a strange statement. But yeah, it's linearly dependent. 0 depends on 0. Let's extend this. Suppose we have n vectors, v1, v2 through vn, and they're linearly independent. So I'm telling you these vectors are linearly independent. If I add the 0 vector to this set, is this set still linearly independent? So think about that for a second. Pause the video. Okay, so it turns out that they're linearly dependent. Why is that? Well, if I put 0 plus, I'm going to put a C1 here, Z2 V1 plus C3 V3, so on. Set that equal to 0. You could put 0 in for all of these. So 0 V1 plus 0 V, this should be a V2. I don't know why I skipped. Oh, I see, because I got a little confused here. Sorry about that. Let me fix that. This should be C1 0, C2 V1, C3 V2, Cn plus 1 Vn, because I need to have n of these. You could also call this one C0, and this one would be C1, C2 to Cn. But notice if I put in 0 for each one of these and anything else for C1, so let's put something non-zero here like a 8. This is a linear combination of these vectors, and this C1 is not 0. even though C2 through Cn is 0, I found a linear combination that's set equal to 0 where at least one of the Ci's, which is this one right here, is not equal to 0. And because of that, this is linearly dependent. Even though these don't depend on each other, I can put 0 in for each one, but the fact that I'm adding the 0 vector, it makes the set linearly dependent. Let's move on to a vector space that is not Rn. So let's say V is equal to the polynomials of degree 2 or less. So remember, this is equal to, a0 plus a1x plus a2x squared, where a0, a1, and a2 belong to the real numbers. What I want to know is, are these three vectors linearly independent inside V? Well, we're going to use the definition. So what we need to find is there a C1, a C2, and a C3 that are not all 0. Make this a little bit smaller. That satisfy that this linear combination is equal to 0. If we can find a C1 or a C2 or C3 that's not 0, then they are linearly dependent. All right, what I'm going to do is I'm going to regroup these. I'm going to get everything with an x squared together, anything with an x together, and anything that's just a number together. So you're going to distribute this. So you're going to have c1x squared minus 2c1x plus 3c1 plus 2c2x squared plus c2x, and so on. That's equal to 0. Okay, now group them and factor out like this x squared from it. So let's get everything with an x squared. So we have c1 plus 2c2 plus c3 x squared then everything with an x, negative 2c1 plus c2 plus 8c3 and then all of the numbers together. So 3c1, 8 c2, and 7c3. And let's put a 1 here. That is equal to 0. But the 0 vector inside this vector space, well, that can be expressed as 0 plus 0x plus 0x squared. So now we're going to set the pieces equal to each other. So this c1 plus 2c2 plus c3 with the x squared, that's going to be equal to this 0. And then this piece in front of this x has to be equal to 0 because that's in front of the x. And then this piece is equal to 0. So let's write that. here. So I'm going to have a system. All of these are equal to 0. And we want to solve this system because we want to figure out what C1, C2, and C3 are. So then we make a matrix. Sorry, I don't know why my pen is dragging like that. Let's try to, there we go. Make this augmented matrix. And now we put this augmented matrix into reduced row echelon form. Now I'm not going to do that. You can do it as an exercise. I'm not going to go through all the steps because we've done it several times. So I'm just going to put the reduced row echelon form for you. Okay, and we see that C1 is equal to 3C3, C2 is equal to negative 2C3, and C3 is free. Solve for the pivots. And so our null space of this matrix is the span of the vector 3, negative 2, 1, because this is 3R, negative 2R, R. And you can see, because the null space is not 0, this implies they're linearly dependent, just by using the definition. I want you to also notice that when I made this matrix, we can think of this as V1, V2, V3 like we did before. But look at this compared to the original vectors. So we had 1, negative 2, 3. Look at the coefficients in front of this. This is a 1, a negative 2, and a 3. Here we have 2, 1, 8, 2, 1, 8, 1, 8, 7, 1, 8, 7. So what we're doing is we're making this, let's say this is 1, negative 2, 3. This is corresponding to x squared. This is corresponding to the coefficient in front of x, and this is corresponding to the coefficient in front of 1. So that's another way to think of this. But grouping like this is perfectly fine as well. You're going to get the same answer.